For most of my life, Maxwell's equations were just wallpaper to me. You know the ones. 4 lines of symbols on the wall of the physics building, on the smug t-shirt in the textbook chapter you quietly skipped. And every single time I saw them, I did the exact thing you probably do. I nodded like I got it, and I kept walking. In the early 1800s, electricity and magnetism lived in separate worlds. Electricity meant wild sparks, lightning, and static. Magnetism meant lodestones, iron, and compasses. No one thought they were related. Then, on April 21st, 1820, at the University of Copenhagen, Hans Christian Ørsted ran current, simply moving electric charge from a voltaic pile through a wire. Suddenly, the needle deflected. With no magnet nearby, electricity had generated magnetism. Ørsted published this in Experimenta circa effectus electricitatis in magnetem. He proved they were connected, but how? How did that invisible influence cross empty space to push the needle? To answer that, we must meet a boy born to a poor London blacksmith in 1791. Michael Faraday had almost no formal schooling. Apprenticed to bookbinder George Rebow from 1805 to 1812, he bound scientific texts and devoured their contents. Through sheer persistence, he went from washing bottles at the Royal Institution in 1813 to director of the laboratory by 1825. He became the greatest experimentalist in history. Yet he never learned calculus before his death in 1867. If you think formal math is required for discovery, Faraday proves that pure physical intuition can reshape our universe. On October 17, 1831, Faraday turned the puzzle upside down. If electricity made magnetism, could magnetism make electricity? He slid a bar magnet inside a coil of wire. Nothing happened. But when he moved the magnet, the needle jumped. When he stopped, the current vanished. Stillness did nothing. Change was the secret. This is induction, a changing magnetic field driving current. That former bookbinder is the reason you have electricity in your wall today. Coal, wind, and nuclear plants all do the exact same thing: spin magnets past coils. To explain how this force crossed empty space, Faraday pictured invisible lines of force filling the air. He had invented the field. Academic physicists found these sketches from a bookbinder embarrassing. They wanted formulas. Faraday had the physical truth, but he desperately needed a translator. That translator was James Clerk Maxwell. Born in Edinburgh on June 13, 1831, he had the elite mathematical training from Cambridge that Faraday lacked. But Maxwell did not replace Faraday's hand-drawn field lines with cold, abstract formulas. He did something much better. He took those invisible fields completely seriously. In 1865, he published a dynamical theory of the electromagnetic field, translating Faraday's physical intuition into a massive web of 20 equations, which physicists later condensed into just 4 laws. Think of them as a map of our universe. How do they work? Let's decode them together without any calculus. So, what do these laws actually say? First, electric charge fills space with an electric field, pointing outward from positive charges and inward toward negative ones. Second, magnets never have single poles. If you snap a magnet, you just get 2 smaller paired magnets. Magnetic lines always form closed loops with no isolated source. Third, changing magnetic fields create electric fields. And fourth, electric currents produce magnetic fields. That last one sounds simple, complete. But there is a quiet, devastating hole in this final rule. A gap that threatens to break the entire mathematical universe Maxwell was trying to build. Picture a capacitor, two metal plates separated by an empty gap. When charging, electricity flows through the wires, creating a magnetic field. But what happens inside that gap? Nothing. No charges actually cross. If you draw one mathematical surface around the wire, there's a field. Draw it through the gap, and the field vanishes, then reappears on the other side. Maxwell refused to accept a universe with broken mathematics. Without new data, he made a daring repair. A changing electric field across the gap must act like a current, even though no particles cross. This changed everything. A changing magnetic field creates an electric field, which now creates a magnetic field. They leapfrog through space, a self-sustaining wave passing an invisible baton through the dark. Maxwell calculated the wave's speed using two simple constants measured from wires and magnets. The result was 300,000 kilometers per second, the exact speed of light. In that quiet moment, he realized light is electromagnetism in motion. We expect waves to ripple through a material, so scientists assumed light traveled through an invisible substance called the ether. In 1887, Albert Michelson and Edward Morley compared perpendicular light paths to detect an ether wind. They found nothing. This productive failure proved electromagnetic fields travel entirely on their own. Sadly, Maxwell never lived to see his fields vindicated. He died of cancer on November 5, 1879, at 48. 8 years later, Heinrich Hertz used a spark gap in Karlsruhe to trigger sparks in a separate wire loop. By reflecting and bending these waves, he proved Maxwell was right. Hertz reported no immediate use for his waves, yet they now power your Wi-Fi, phone calls, and radio. Those equations are no longer just wallpaper. They are the path to Einstein's universe. Subscribe to watch our upcoming video on special relativity. Hertz's waves were just the beginning of a spectrum that stretches like a giant piano keyboard for miles in both directions. Visible light, from 400 to 700 nanometers, is a single tiny octave. The rest is radio waves stretching for meters, microwaves, infrared, ultraviolet, X-rays, and gamma rays. They are the exact same phenomenon, differing only in wavelength, the crest-to-crest distance, and frequency. But why this exact speed? The constants governing light are properties of empty space, not light itself. Because this speed is built into space, it must be the same for everyone, forcing space to contract and time to dilate. Maxwell's equations are no longer just wallpaper. Subscribe to watch our next video on special relativity. No longer just wallpaper, these equations are the blueprint of reality. Every beam of light is a self-sustaining wave, guiding us directly into Einstein's universe.